Welcome to this lecture of thermodynamics, and this concludes the discussion we have been having on kinetic theory and later on thermodynamics. So, again as usual, I shall start by recapitulating what we have learnt in the last lecture, and then I will give you some topics, discuss some special topics which could be slightly advanced, but at the same time they will help you to have a deeper understanding of whatever thermodynamics I have discussed in last 4 lectures. So, again recall second law of thermodynamics, that is what the essence of last lecture. Two statements which are equivalent. One is Kelvin-Planck statement. Kelvin-Planck statement refers to engine and tells us that we cannot have an engine whose efficiency is 1. Okay? So, it says no cyclic process is possible whose sole result is the absorption of heat from a reservoir and the complete conversion of heat to the work. That means output always be less than the input. Okay? Second is Clausius statement, which again refers to another version of second law, which is equivalent to this Kelvin-Planck statement I have written here, but it refers to the refrigerator. It tells us that I cannot have a refrigerator whose coefficient of performance is infinity. That means I cannot construct a refrigerator which absorbs heat from a cold reservoir and dumps the entire amount of heat to a hot reservoir. It is not possible. I have to do some work on the refrigerator to make it work in a closed cycle. Okay? Then I talked about Carnot engine, which is a reversible engine. I told you repeatedly what do I mean by reversible engine. Dissipationless, working substance I chose to be 1 mole of ideal gas, but also we discussed this is not essential. Ideal gas specific heat is independent of volume and temperature and any other quantities. It is 3/2 Nk if I consider 1 mole of monoatomic ideal gas. In that case, calculation becomes very simple. Okay? Engine works in a complete cycle. What was important? There was a hot reservoir at a temperature T1 and a cold reservoir at a temperature T2. Efficiency should be maximum, but we calculated the efficiency, it was not unity. Okay, let us proceed. So, Carnot engine was operating in 4 processes: isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. This brings me back from P1 V1 T1 to P1 V1 T1. I complete a closed loop in my PV diagram, a closed loop. And there were few comments. These processes can be executed in any order, ensuring the initial and final states are the same. P1 V1 T1 initially, P1 V1 T1 finally. We calculated the work done and heat absorbed, and internal energy being a state function, its change is 0. So, we did not really care about the internal energy. Okay? So, what did we find out? What is the remarkable result? Remarkable result is the following, that efficiency is 1 minus T2 by T1. What was T1? T1 is the temperature of the hot reservoir, T2 is the temperature of the cold reservoir, and the engine is operating in a closed loop, extracting heat from the hot reservoir, dumping heat to the cold reservoir, in the process doing work W. Okay? And this efficiency cannot be unity, because then you have to set T2 is equal to 0 and T2 is equal to 0, you cannot set, and that is why efficiency is finite, but it is maximum. So, then we proceeded to discuss Carnot theorem. Given two heat reservoirs, which means T2 and T1 fixed, a Carnot engine has the maximum efficiency. Any irreversible engine will have less efficiency than the Carnot engine. Okay. Furthermore, efficiency of all reversible engines working between two given reservoirs, that means T1, T2 fixed, is the same. Secondly, it is independent of the working substance or the operational details, the way I executed my thermodynamic operations. This is what I called Carnot theorem. And I gave you some argument regarding this Carnot theorem, that is the following. I had two given reservoirs, which is having temperature T1, T2, this one is hot, this one is cold. I ran two engines, one is Carnot. Carnot was being operated as a refrigerator, and then parallelly within the same reservoirs I had an irreversible engine. Okay. This picture reminds us what we were doing. Carnot operated as a refrigerator, which is absorbing Q1 minus W amount of heat from this reservoir, dumps a Q1 amount of heat to the hot reservoir. Whereas the irreversible engine, it extracts Q1 amount of heat from the hot reservoir, W amount of work it does, and rest of the heat Q1 minus W prime it releases to the cold reservoir. So, that was the situation. I argued that these two taken together actually works as an engine which absorbs W prime minus W amount of heat from this reservoir and converts it entirely to work. Then we argued it is not possible, it is violating second law. If I assume W prime is greater than W. So, argument was W prime cannot be greater than W. So, W prime is never greater than W. If W prime is greater than W, I violate second law. This system violates second law. This was the argument. Once we convinced ourselves that W prime cannot be greater than W, we proceeded, and series of mathematical arguments told us that efficiency of Carnot engine is greater than efficiency of the reversible engine. That is the summary. So, we cannot have W prime greater than W because that makes second law violated. We cannot do that, hence eta C must always be greater than eta irreversible. That is the summary of whatever we did in the last lecture. Let me now proceed and give you some concepts, some notions which are different, slightly advanced, but I told you in the beginning these topics, like I am going to introduce entropy, will be very useful for further studies and of course understanding thermodynamics by heart. Okay? Entropy. So far we have been talking about thermodynamic variables U, internal energy, volume, temperature, pressure, some of them extensive. We discussed what do I mean by extensive at length. These are intensive. Okay. Now I bring in a new thermodynamic variable which I call entropy. It is an extensive thermodynamic variable. Entropy, if I consider usually, let us say, isolated system, is just a name. Do not get baffled by these names. What an isolated system mean? It means my system plus reservoir. System and reservoir taken together constitute an isolated system. So, entropy can be written as a function of U, internal energy, N, number of particles, and volume of the container. So, this is entropy. I will give you more mathematical form soon, but it can always be expressed as a function of pressure, temperature, and so on. Okay. Given an equilibrium thermodynamic state, I know equilibrium thermodynamic state is characterized by pressure, volume, and temperature. And similarly, if I have an equilibrium thermodynamic state, whenever I mean equilibrium state, has a definite value of entropy. Okay, this is important. And entropy is a state function. What does it mean? Entropy depends upon the state of the system, P, V, T, etc., as was internal energy. If you remember, I always told you heat absorbed or heat released depend upon the thermodynamic path, thermodynamic processes I execute. Work done, heat absorbed. That is why I was always writing them as delta Q, delta W, but I was writing du all the time, because if I do a thermodynamic process, then change in internal energy only depends upon the initial and final state, difference between the final value and the initial value of the internal energy. So, in that sense, entropy is also a state function. Okay? But there is a difference between internal energy and entropy. I told you that when you talk about internal energy, you really don't care where do you set your zero of energy. This is not true for entropy. In the limit of absolute zero temperature, entropy vanishes. Okay? Entropy goes to zero if temperature goes to the absolute zero. This is sometimes referred to as third law of thermodynamics. Now, I will consider a reversible process. Let us consider that a small amount of heat transferred to a system which is at a temperature T, very small amount. You can ask the question, what is the change in the entropy of the system? This is the change. You see, it is delta Q over delta T amount of heat. Sorry, this delta should not be there. I erase it. It is delta Q over T. This is the amount of heat supplied and this is the T temperature at which the system is maintained in equilibrium. That means here I am assuming delta Q tends to 0. Okay. This is the small change in entropy in this process, which I have said is a reversible process. But in general, I can have heat exchange which takes the system from T1 to T2, then the expression or change in entropy will be like this: SF minus SI final value minus the initial value, which refers to change, but this is a finite process, this was an infinitesimal process, but both reversible. This is the expression delta Q over T integrated from T1 to T2. This is my change in entropy. See, entropy change does not require that T is to be fixed. It need not be an isothermal process. Okay? That is why I cannot simply write is as a total change by the temperature. Okay? I have to integrate from T1 to T2. Okay? Now, what you clearly see that delta Q is important. It is important that system absorbs heat or system releases heat to its entropy, so that its entropy changes. So, in an adiabatic process, we know delta Q is equal to 0 in an adiabatic process, hence entropy change is 0. Okay? Often I will refer to adiabatic processes as isentropic process. We know isothermal, which keeps temperature fixed, isobaric, isochoric, and adiabatic now onwards I will refer to as isentropic, because in an adiabatic process change in entropy is equal to 0. Any irreversible process you may have in mind, you can argue that this quantity Sf minus Si is always greater than the quantity I calculated for a reversible process. So, I can think of a reversible process between temperature T1 and temperature T2. I can calculate the entropy change. Irreversible process, I go from T1 to T2, same values, but entropy change will be more. So, this is summary of entropy. Entropy is an extensive thermodynamic variable. Given a thermodynamic equilibrium state, there is a definite value of entropy. If I consider reversible processes and a small amount delta Q tending to 0 heat is provided to the system, then there is a change in entropy, rather increase in entropy. If I provide heat maintaining a temperature T, then change in entropy will be delta Q over T. In general, I will have an integral from the initial temperature to the final temperature, that will give me the change in entropy. But if I have an adiabatic process, there is no heat exchange. As a result, entropy change is 0, okay, and I shall call it isentropic process. Okay. In any reversible process, entropy change will be more than the entropy change in corresponding reversible process. Okay. Some sense you will find out the statement that entropy is very loosely speaking related to the randomness or disorder of the system, and we lose information about the system when entropy increases. What do I mean by that? Okay. Let us take 3 levels, energy levels, if you like, you know Bohr theory a little bit of, okay. You can think of 3 Bohr levels which electron can occupy. If I know with probability 1 that electron in level 1, okay, with probability 1, then entropy will be 0. But if there is a finite probability of electron being in level 1, level 2, level 3, then entropy is greater than 0. It is a positive value, but at the same time I am losing information. When I was knowing for certain that system or the electron is in the level 1, entropy was 0. The probability of occupying other states increase, entropy increases. That is why I said we lose the information about the system when the entropy increases. Okay. Now, there comes a very fundamental law of nature. This is how one proposes the second law in modern books. Consider an isolated system, system plus reservoir. Okay, that's my isolated system. In any allowed thermodynamic process, okay, delta S will always be greater than 0. Delta S refers to the change of entropy of the system plus the change of entropy of the reservoir. So, S delta S of system plus delta S reservoir, these two taken together must be greater than equal to 0. This is the second law of thermodynamics. Everything what we have learnt about second law is encoded in this simple mathematical expression. Delta S, if you like, I write a total so that you do not lose track with system and reservoir. So, this is S total, total entropy change is greater than equal to 0. Okay. What does it mean? And when does the equality sign hold? Equality sign holds only when there is a reversible process. Okay? It is only in reversible process. Any irreversible process you may have in mind, total entropy always increases. Okay? Entropy cannot be dissipated. Once entropy is generated, it is there for an isolated system. Okay? Now, you may often heard this statement, entropy of the universe is increasing. This is what is implied here, which means if you consider a universe to be an isolated system, there are plenty of processes which generate entropy, but entropy cannot be dissipated, and hence total entropy of the universe is always increasing. So, two things in this slide I would like to summarize. Entropy increase means loss of information, as I have illustrated giving these three levels. If I know system is in any one level with probability 1, entropy is 0. If it is distributed over different levels, entropy increases. Secondly, second law you can write in the form delta S total is always greater than equal to 0 in any thermodynamic process. Reversible process, delta S total is equal to 0, and entropy of the universe is always increasing because you can generate entropy, but you cannot dissipate entropy. This is very, very fundamental form of second law. Now, I would like to say briefly one more thing. Remember, entropy is a state function, and what was our first law? First law was du plus pdv, and I am talking about reversible processes. What is dq? We have already seen d cube by t is ds. Remember, I am writing ds because s is a state function, I told you repeatedly. So, I can write my first law in the following form: tds is equal to du plus pdv. So, this is often called the second law of thermodynamics in the mathematical form, which is nothing but the first law, but I have brought in the concept of entropy, which is a state function, and replaced delta q, which is a path dependent function, thermodynamic process dependent function, with entropy. So, I have this equation now, TdS is equal to du plus pdv, where this is mechanical work done. I am assuming everything mechanical work, everything reversible, of course quasi-static. So, this is all about entropy I wanted to say. Then I will talk about something called TS diagram. Okay? That means thermodynamic processes are to be drawn on TS plane rather than PV diagram or VT diagram. It is useful. You can see why it is useful. It is useful because we have talked about two processes so far, at least in the context of Carnot engine. Okay? What are these two processes? Isothermal. Isothermal means temperature is fixed. So, this is isothermal. It is a parallel line, temperature fixed. And secondly, isentropic, adiabatic, which means entropy is fixed. Okay? So, this represents an isothermal process. Isothermal this is adiabatic, which I shall call isentropic. Okay? Now, TS diagram is useful in the following sense, which I will argue. PV diagram, area under the curve provides the work done on or by the system, that we have learned. TS diagram on the other hand, as you will see in a closed loop, in TS diagram will provide you the net heat exchange. This you can easily argue, which I will not show the argument. I have already told you adiabatic process, isentropic process, isothermal process, entropy changes keeping temperature fixed. Okay? Remember, this is very important. Change of entropy of the system and the reservoir both taken together is 0 in a reversible process. Okay? So, with this input we will start to proceed Carnot engine and draw the TS diagram for a Carnot engine. Let us recall the PV diagram. Okay? So, this is my PV diagram. This was my step 1, step 2, step 3, step 4. I was starting from P1, V1, T1. This is an isothermal process that takes me to P2, V2, T1, followed by an adiabatic or isentropic process. So, that takes me to P3, V3, T2. Here I reach the temperature of the cold reservoir. Then there is a contraction which takes me to P4, V4. This is again isothermal process. This is T2. Then an adiabatic contraction takes me back to P1, V1 and T1. So, this is my isothermal, this is my adiabatic, again isothermal, again adiabatic, heat absorbed Q1 and heat released is Q2. Okay? Now, we will draw the TS diagram for this corresponding Carnot engine. Okay? We should proceed to draw the TS diagram for this Carnot engine. Okay? So, this is your T, this is your S. I am plotting temperature as a function of entropy or the other way around. So, first process was isothermal. So, let us fix two temperatures, let these be T1, this be T2. Okay. First process was isothermal, in which entropy changes. In this case, system is absorbing heat, Q1 amount of heat, so entropy will increase. Okay. then followed by an adiabatic expansion in which entropy cannot change. So, this is step 1, this is the step 1 here, this is step 2 which corresponds to step 2 here. So, 1, 2, this is step 3, this is the step 3 here, isothermal process, but it was a compression, that is why heat was released, Q2 amount of heat, and step 3, that is why entropy decreases but comes back to this value, and then you have an isentropic or adiabatic process which is step 4 here. This gives me this step 4 here. Okay, I should draw it here rather. Okay, so you see that the TS diagram for a Carnot engine, this is the PV diagram, and this is the TS diagram of the Carnot engine. Okay, TS diagram. You see, TS diagram looks much simpler only because of the fact isentropic processes are straight lines like this and isothermal processes are straight lines like this. You see, you have a rectangle. You had a complicated geometry here, instead in TS diagram you have a rectangle. Okay? So, now how can you calculate the efficiency? Okay? You see, remember this curve and this curve. These two, there is no entropy change. Okay? 2 and 4, there is no entropy change because these are adiabatic processes and there is no heat exchange. Okay? So, now step 1, heat absorbed is Q1, temperature was maintained at T1 is the temperature of the hot reservoir. So, delta S1 is equal to Q1 by T1. Okay? Adiabatic process steps 2 and 4, delta S is 0. We do not have to care about these two processes. Step 4 on the other hand, step 4 is here. Okay? Equivalent. You see, the step 4 is again adiabatic, but step 3 one has to be very careful. Okay? So, step 3 one has to calculate. Step 3, heat absorbed is Q2 and temperature is T2. So, delta S2, let me call it, is minus Q2 by T2. So, heat absorbed in this process, entropy change delta S1 is Q1 by T1. 2 and 4 adiabatic processes, delta S is 0. Step 3, heat released. I wrote absorbed because I gave a minus sign here. Let me clarify, heat release Q2 at a temperature T2, delta S2 is minus Q2 by T2. Now, remember, I should tell one statement very clearly. We are focusing on the system. In any process, the net change in the entropy of the system plus reservoir is 0. That means, here entropy of the system is increasing, but reservoir is losing heat. Its entropy is decreasing and total entropy change is 0 because it is a reversible process. Similarly, here entropy of the system is decreasing, but entropy of the reservoir is increasing because system is releasing heat to the reservoir. Okay? So, but it is a closed loop. So, TS diagram was giving me a closed loop. I come back to the same position. Okay? So, in the closed loop, net change of the system is 0. Also, is 0, and add them, you will always find out total change of the system plus this or y is equal to 0. So, S total of the system is Q1 T1, this quantity, Q2 T2, which is this quantity, which should be equal to 0. So, Q1 by Q2 is equal to T1 by T2. So, what is the efficiency? Efficiency is 1 minus Q2 by Q1, which immediately gives me 1 minus T2 by T1. So, that is the purpose of this discussion. I told you that if I use TS diagram instead of PV diagram, I have these processes represented by straight lines in the TS diagram, okay? And then immediately I can work out the efficiency of a Carnot engine, which is given by 1 minus T2 by T1. So, same result we obtained using the TS diagram, okay? This is all I wanted to say about entropy, but today's lecture still we have some time left. I would like to do some problems for you and give you some food for thought so that you can learn on your own few advanced topics. So, first let us do a problem. This problem is quite an illustrative problem which involves an imaginary ideal gas engine, okay, and the assumption I will make, Cp and Cv are always constant, okay, and now let us draw the corresponding PV diagram, and I leave it to you to construct the TS diagram, okay. So, PV diagram is the following. There is a V1, there is a V2, there is a P1, let us say P1 and P2. There is a process which is like this, and there is a process which is like this, and there is a process which connect these two. The slope should be monotonic, my drawing is bad, rather it should be like this. I erase the upper curve, okay. So, immediately see that what is this processes? This keeps your pressure constant. So, this is isobaric. This is obviously volume constant. We know what is this. This is isochoric, and finally this is my isentropic or adiabatic process. I ask you the question, I put the arrows like this, isobaric followed by isochoric and then finally adiabatic. I ask you the question, very simple question, that calculate the efficiency of this, okay. Calculating efficiency is not difficult, you have to calculate the work done. First remember, this process V is kept fixed, so work done is 0, okay. Whatever work done will be here and here, okay, but I will not calculate the work done, that I also leave for you to chalk out what is the work done, because we know the work done, how to calculate it for both isobaric and adiabatic processes. I would rather calculate Q1 and Q2. Let us see, heat absorbed. Okay. Heat absorbed in which process? Here you see pressure is increasing, which means temperature is increasing. Let us call this temperature T1, this temperature T2, this temperature is T3. Okay. Now, in this process, how much heat will be absorbed? Cv, volume is kept fixed, Cv T3 minus T2. T3 must be greater than T2 because pressure is increasing. T3 greater than Tt because pressure is increasing. Keeping volume fixed. So, this is the process which is involved in heat absorption. Now, heat released should be this process. Heat released, okay, I am referring to the magnitude of it. Okay, should be pressure is kept constant. So, Cp and T1 minus T2. It is negative T2 minus T1, but I am referring to the magnitude only. So, remember this is heat released. Okay. Now, once I have heat absorbed and heat released, I can immediately calculate what is the efficiency of my engine. Okay. Efficiency will then be given by 1 minus Q2 by Q1. This is my Q2. Remember again, it is the magnitude. Okay. So, remember what is the engine? Ideal gas engine, okay, and then CPCV I have assumed constant, does not depend on anything as happens for ideal gas, as you know. So, now you have one isobaric process, one isochoric process, one adiabatic process. I asked you calculate the work done, that will be in this process and this process no, volume is kept fixed. Okay. Second, find out the TS diagram, PV diagram I have given. So, I calculated heat absorbed, heat is absorbed in this process because keeping volume fixed I am changing pressure. You know, if I keep volume fixed, P is proportional to T, pressure increases mean temperature increases and the heat absorbed will be Cv T3 minus T2. I have assigned temperatures. Okay. Now, heat is released in this process because it is isobaric, volume is decreasing keeping pressure constant. So, T2 will be less than T1. I have written the magnitude of the heat released at Cp T1 minus T2, which is Q2. Now, let me try to calculate the efficiency 1 minus Q1 by Q2, which is nothing but 1 minus Cp T1 minus T2 by Cv T3 by T2. This gives me the answer, but it is not a very good answer because the problem gives me V1, V2, P2, P1. It does not give me T1, T2, T3. So, I should be able to express everything in terms of given quantities in the problem. So, let us proceed. Efficiency I can write as eta 1 minus Cp T1 minus T2 by Cv T3 minus T2, which I can simplify as 1 minus gamma T1 minus T2 by T3 by T2. Okay, these we have written previously, but this does not give me very nice result. As I told you, I have to express in terms of P1, P2, V1, V2. You can easily see from here T1, it ideal gas. So, I will always have PV is equal to RT satisfied. So, I will have T1 is equal to, I will be careful, P1 V1 R. Okay. Similarly, if you look at T2 I can write as P2 V2, sorry, it should be P1 V2 by R. T3 similarly I can write as P2 V1 over R. I am going to substitute this. See, this is P2 V2 as per my notation. This is P1 V2 by R. This is P1 V1 by R. So, let me substitute in this expression and see what I get. So, efficiency eta will be given by 1 minus gamma P1 V1 minus V2 V2 P2 minus P1. So, all I have done, I have replaced temperature, substituted for temperature for 1 mole of ideal gas. I always have PV is equal to RT satisfied, and I know coordinates of the point which are denoted by temperature T1, T2 and T3 respectively. So, immediately one can simplify life and one can write out the final expression, which is V1 by V2 minus 1 upon P2 by P1 minus 1. So, this is the efficiency of the engine I have been talking about. Okay. This is one example of doing some problem using the simple PV diagram. To end this discussion, I will have 2 more comments and I will leave 2 problems for you to do. For example, if I give you a TS diagram, okay, now it is a TS diagram, not PV diagram. This you can say problem 2. Okay. Here you have a TS diagram and I give you 3 processes. All these are straight lines. Okay. So, let us say my arrows go like this, this and this. I ask you identify the processes. Okay. So, this one you immediately know entropy is not changing, temperature is. So, this is adiabatic or isentropic. What about this one? This one we can easily find out because temperature is constant, is isothermal. This process, what is this process? This is not adiabatic, it is a straight line I have drawn. Okay? So, this process can be isochoric or isobaric.
Or it could be any other process, a composite process, for example, which you can figure out from the corresponding PV diagram. However, what is important here, given this cycle, calculate the efficiency of this engine. That you should be able to do from the TS diagram itself. Now, you may ask me how to distinguish between an isobaric and an isochoric process on a TS diagram. This is what I am going to discuss now.
In a PV diagram, you can always identify which one is adiabatic, which one is isothermal by looking at the slope. Question is, in TS diagram, identifying isothermal or adiabatic isentropic is very easy. What about isochoric and isobaric. Okay, they will have different shock. So, the comment I would like to make that you should note these following things, that a isochoric curve, remember I am talking about isochoric curve, if you calculate the slope it's T over CV. Isobaric curve slope will be T over Cp. Remember, this is with respect to the TS diagram. So, TS diagram, del T del S, change in temperature with entropy if volume fixed is greater than del T del S over P. Okay, slope of this isochoric is higher because Cv is smaller than Cp. Okay, so if I give you two curves, you should be immediately able to tell me that this is isochoric, this is isobaric. Remember, I am referring to TS diagram. So, problem 2 involves TS diagram, identify processes in TS diagram, calculate the quantities, adiabatic and isothermal very easy to find out, whereas isochoric and isobaric, once again draw two curves, look at the intersection and find out the slope. From the slope, see whether this condition is satisfied or not. If it is, you know this one having higher slope, steeper slope, okay, will be your isochoric process.
To summarize, if I have a TS diagram, this horizontal curve obviously isothermal, this one is isentropic, there will be isobar and isochor. So, this will be the isobar and this will be the isochor. That is what I have discussed based on the argument I have given previously. So, let me conclude by giving you one more cycle in the TS plane, which is following. Very close to the cycle I drew in the previous slide. Again the question will be calculate the efficiency. Calculate the efficiency from the TS diagram itself. I can say this is T1 if you like, this is T2.
So, this is where I would like to end this set of lectures of kinetic theory and thermodynamics. I have followed two books, one is the NCERT book, other is book by Professor H.C. Verma, and these two books and also something not covered in your standard books, but I wanted to give you some insight in the problems, and some of the problems I discussed are very deep. If you understand them by heart, you will learn the subject better. Okay? So, purpose was to tell you the microscopic origin of kinetic theory and macroscopic origin of thermodynamics, but eventually all should lead to same set of results. We have been using PV is equal to RT for 1 mole of ideal gas always. So, two different approach, but fundamentally we want to get the same set of results which are experimentally verified, and which are reproducible in our laboratories. So, this ends our class lecture sessions on kinetic theory and thermodynamics. I thank you all very much for your attention.